of pages of this chapter particularly, or don't go by the number of sessions that we are going to conduct of this chapter. Go by the feel of the chapter, go by the intensity of the chapter, go by the number of things and the understanding that you're going to get from this chapter. And hence, it is no exaggeration to say this very chapter is the heart and soul of chemistry. So let's delve into the topics that we have to talk about today. So of course, I will start with the timeline of the classification of elements, but our agenda is to reach modern periodic table. I will also give you the systematic nomenclature of how to go about naming an element, right? So a lot of interesting things waiting for you. Let's delve deep into it. If I have to start this chapter, first question is, of course, indispensable from the very name of the chapter, that why there is a need of classification of elements. Well, the answer to this question is as simple as why there is a need of classification, let's say in a library, or why there's a need of classification in, let's say, your wardrobe, or let's say why there's a need of classification in, let's say, your kitchen. Ask your mom, she will better give you the answer that why spoons has to be just here, why the spices has to be just here, why the big containers has to be just here, and anything, any little change there and you will be in a mess, isn't it? Hence, we need to organize. And here I would like to give you a disclaimer that always study also in an organized manner. If you do things randomly, like let me pick up electronic configuration first, and then I will go to the first thing, that is Rutherford model, and then let me come to the quantum mechanical model, and then let me go back to the scattering experiment, that will be very, very chaotic. Realize the need of how and why things needs to be organized. So we need to organize, of course, and if we talk about organizing our bookshelf or organizing our kitchen, we know the life becomes much more easier. If you see a library, of course, properly books are aligned and it makes our job much more easier. We can easily study. Now, if I talk about elements specifically, here it becomes very easy. Whichever book you want to take out, you can easily take out. But in chemistry, things are going to be even more beautiful if you classify. Why? Because we are not just interested in studying 118 elements, we are interested in studying their compounds also. So many elements, of course, have their individual so many compounds. So if we classify elements and study just the classified group, or let's say if we are organizing things, okay, and then studying them, that makes our job easy, study easy, connecting the dots easy. So it's very important to organize, and hence there is a need of classification, right? But I want you to go and see the chapter's name once again, and you will see there is something very important lying there, which is periodic classification. We understood there is a need of classification, but why the name periodic classification? Of course, there might be some properties which are repeating itself. Hence the name periodic, right? So this word periodic is very important, and we are using this term because it indicates that properties of elements that repeat themselves. So if we arrange things according to a proper manner, according to an organized manner, and we study the classified group, let's say, we understand the whole group rather than understanding the elements specifically. So what is this groups? What is this period? What are blocks? Lots of questions must come in your mind when I talk about modern periodic table. But before I simply jump to modern periodic table, I want you to know the developments that were made, and you have done them in your junior classes. right? So I will not delve deep into it. You have to study. You have already studied it. So let's brush it up and quickly see the whole agenda which is waiting for you, which is modern periodic table. So if I have to show you the developments, of course, you know the major ones: law of triads, Newland's law of octave, Manleaf periodic table, and finally modern periodic table. Let's quickly look at each one of them layer by layer, one by one. So Daubernier law of triads is a very simple development which was a stepping stone in the classification. And if I talk about how he grouped things, he made a group of 3, which will do no help to us when we reach so many elements that we have today. So of course, you can see the year it has come in. So the year is way back. Of course, very less elements were discovered by then. And hence, this was a milestone because somewhere we could proceed towards arranging the elements, and he did arrangement in such a way that the central element will have the atomic weight which will come out as an average of the other 2 elements. Very simple. So the atomic mass of the central element was merely the arithmetic mean, simply average of the atomic masses of the other 2 elements. Let's check it. So you can see that lithium has an atomic weight 7, potassium has atomic weight 39. If we take the arithmetic mean of the 2, we get 23, which is the atomic weight of the central element sodium here. So is what I can apply to calcium and barium. Calcium atomic weight 40, barium atomic weight 137, and the arithmetic mean would give us 88, which is the atomic weight of strontium. We can extrapolate the same thing to chlorine and iodine, and we will get the atomic weight of bromine. Of course, if I ask you, are there drawbacks? Of course, there are drawbacks. The whole concept was actually dismissed by calling it just a mere coincidence. So, yes, it was not applicable everywhere, and of course, it was applicable to very few places. Hence, maybe it's just a coincidence. But we must appreciate the milestone set in the field of classification of elements. Next one is the Newland's law of octaves. Octaves, you know, are the musical notes like we have sa re ga ma pa dha ni sa. So arrangement of the elements in increasing order of their atomic weights, noting that the properties of every 8th element is similar to the first element. Okay, that's something that you know. I want you to observe the year. The year has passed as compared to the previous one. Hence, number of elements discovered has increased. Yet, if you see that his arrangement of elements in terms of the musical notes, yet you will see that it's applicable only till calcium. Okay, so of course better but not best. Hence, of course, there are drawbacks. Arrangement of elements up to calcium was possible out of the 56 elements known at that time. Do we need better classification? Of course, which came by this genius guy, Manleaf, and Manleaf's periodic table. You can very well see again the year. So we can say that the number of elements are of course increasing. So arranged 63 known elements in increasing order of atomic weight. He was going very well, okay? So the idea was, of course, going very well. You can understand and draw parallel between the timeline that I gave you for atomic structure and the timeline of the periodic classification of elements. And you will understand and realize that why is the term atomic weight written there? Though it sounds so obvious right now to us that it should be atomic number. Manleaf, how could you not know that? It is not that obvious because you have to understand the timeline from which it is coming. All right? Hence, understand and give the credits to this guy Manleaf, who is also regarded as the father of periodic table. So he did something very, very exceptional. The elements with similar physical and chemical properties. So he did not go by superficial way of placing elements. He studied the physical as well as the chemical properties of elements. And what he did, elements with similar physical and chemical properties occupy same subcolumn. So you will see a table coming up when we are talking about Mendeleev periodic table. So again, very similar to the modern periodic table, you will see rows, you will see, of course, columns. So in a similar fashion, there are groups and periods, but not as what we define for the modern periodic table, right? So table you can see right now when I talk about Mendeleev periodic table. And if you would see the table, which I'm just going to show you in a while, the properties of elements are a periodic function of their atomic weights. Please understand, the very line is something that we can use for modern periodic table also by just changing the word weights with number. Just by changing weights with number, and it becomes so sorted. Of course, this is revolutionary, and there were, of course, similar way, the horizontal, when I'll show you the table, observe the horizontal rows and observe the vertical columns, right? And you will see that the properties are periodic function of their atomic weights. But he gave this rule, he gave this statement, but he did not follow it very, very rigidly. Of course, he ignored the order of atomic weights and placed the elements with similar properties together. Like I told you, he was studying the properties. So he kept that funda in mind that things has to be according to the properties, right? So at some places, some of it were differing. So what he did, he placed it not according to the rigidity with following his statement that the properties are periodic function of their atomic weights. Rather than wherever it was somehow not matching, he still ignored the order of atomic weights and placed the elements with similar properties together, which was, it was incredible. Please understand this very, very important things where we actually cocoon ourselves just because we have given a statement. We go to any extent to just match it, but here he has played it very well. He adjusted atomic weights of elements, assuming that they were not measured accurately. What if they were wrong? What if whatever weights they have found out is wrong? According to me, this should be the order. So he was very smart. He predicted the properties of some undiscovered elements and left several gaps. Again, genius of him. Two of them are under aluminium, are called Eka aluminium and Eka silicon. So he realized that some of the elements don't fit in actually, and he realized that there might be some elements which are not discovered maybe, or he realized that what if atomic weights are wrong. So assuming all these hypothetical things, he gave his periodic table, which looks like this. You can see that we have different groups out here. Group 0, 1, 2, 3, 4, 5, 6, 7 and 8. In group 8, you can also see iron, cobalt, nickel placed together, right? And you can also see that there are certain elements that he was very smart at predicting that what if they might be discovered later on. Please observe it out here. Okay, so this is very important, revolutionary, and this is, of course, a stepping stone towards the modern periodic table, right? So are there drawbacks that you see in this table? Of course you can. And you can see that hydrogen did not have a fixed position. There was no regular trend in increasing order of atomic mass while moving along the elements. Isotopes were found later which failed to comply with the periodic table. Please find out out where all atomic mass did not match. All right? Where all it was a hindrance. So now let's take it forward. And of course, we know that we are coming from years back. And of course, as we keep going forward, more research keeps happening, more advancement keeps happening. And hence, this guy, Moseley, did some modification. So according to the Henry Moseley, he observed irregularities in the characteristic X-ray spectra, okay, of the elements, where he found that a plot of root nu. So what we are talking about? We are talking about frequency here, root of the frequency, where nu is the frequency of X-rays emitted against the atomic number Z, gave a straight line and not the plot against atomic mass. All right. So this is very important, that when we talk about Z, things appeared absolutely fine. But when we were talking about atomic mass, all right, things were not fine. Okay. So if we were plotting this, something like this, that root of nu and Z, it was coming out to be a straight line, because this is suggesting us something which was fundamentally wrong when we were talking about Mendeleev periodic table. Of course, the very term atomic weight should have been replaced by atomic number, and then everything would have been perfect, right? So Moseley was the guy who did some study, who plotted graph of the frequency, the root of frequency with atomic number, and found that we should not call for this statement, which is the physical and chemical properties of the elements, a periodic function of their atomic numbers and not atomic mass. Periodic law is essentially the consequence of periodic variation in the electronic configuration. Can you see the dots connecting out here? Hence, whatever we have utilized in the last session of atomic structure will be well utilized in today's session. So, which determines the physical and chemical properties of the elements and their compounds. So, we know different elements are there. We know different elements have different electronic configuration. And also now we know that modern periodic table is arranged in such a way that increasing atomic number, if we keep going by that, we have a pattern coming into picture. So we have a periodicity coming into picture. So, of course, the very fact of atomic number means the number of protons. You know that atomic number is nothing but the number of protons or number of electrons in a neutral atom. Number of electrons, of course, number of electrons means electronic configuration has to be kept. So if I'm saying 1s1, that means it's element 1. 1s2 means element 2. 1s2, 2s1 means element 3. 1s2, 2s2 means element number 4. So you can easily see that as the more number of electron keeps adding, the atomic number keeps increasing and hence the element keeps changing. So, modern periodic table, how the elements are arranged in the modern periodic table. Now you know that they are arranged in the increasing order of their atomic numbers, right? So, the long form of periodic table, the horizontal rows are called periods. Vertical columns are called groups. So, horizontal rows, vertical columns, groups, okay? Elements having similar outer electronic configuration in their atoms are arranged in vertical columns referred to as groups. Okay, so whatever will lie in this vertical column, which is group that we are saying. So whatever element will lie in the same group will have the similar properties. Each period corresponds to the highest principal quantum number of the elements in the period. Okay. So if n is equal to 1, period is 1. If n is equal to 2, period is 2. If n is equal to 3, period is 3. If n is equal to 4, period is 4. So basically you can see that the highest principal quantum number, which was n, higher the whatever is the value of n, will be the value of the period number. Okay? Now, please observe, there are several things waiting for you here. You can obviously see the numbers written 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. We have 18 groups. And all the elements in the same group have similar properties. Okay? Please observe. Also, I want you to observe there are 7 periods. 1, 2, 3, 4, 5, 6, 7. So there are 7 periods. Also, I want you to use your mind and remember electronic configuration that we have done in the previous session of atomic structure, wherein we have talked about different elements have different periodic, different electronic configuration. So basically, if I'm talking about 1s1, that's one element. If I'm talking about 1s2, it becomes another element. 1s2, 2s1, it becomes another element. 1s2, 2s2 becomes another element. So things are obviously in accordance to the electronic configuration and hence the increasing atomic number. Also, now I want you to see that these poor guys out here have not got their space inside the periodic table, which is right here. Something is written and something is written of the same color, and they have been extrapolated outside. Let's see why, let's see how, let's see the technicalities, the subtleties. So let's see the modern periodic table properly in details with the subtle nuances. So you can see that we have 18 groups, we have 7 periods, and we have 4 blocks S, P, D, F. How do you think the name SPDF is coming? Can you quickly tell me? Quickly, SPDF. Do you get a nostalgia of something? Not long ago, we talked about SPDF. Of course, you know that we are talking about here subshells. We are talking about azimuthal quantum number. We are talking about S orbital, P orbital, D orbital, F orbital. How the relation is there between the two chapters now should become strikingly clear. So if I talk about the modern periodic table, I want you to observe once the whole picturization here. Please observe NS1, when we are talking about, we have group 1, NS2, then the whole D, then NS2 NP1, NS2 NP2, NS2 NP3, NS2 NP4, NS2 NP5, NS2 NP6. Let me take some rest. Please observe now. I want you to observe it. Please observe that the elements with the similar electronic configuration are lying in the same group. And the elements in the same group will have similar properties hence. Will there be exceptions? Of course. What is inorganic chemistry without exceptions? There will be exceptions, but we are going to talk very general because let me tell you out here that different blocks that I'm going to talk about. So S block is there, P block is there, D block is there, F block is there. We have separate chapters based on S, P, D and F. So S block is a part of class 11th. In fact, hydrogen is a separate chapter altogether because this poor guy could not get a proper space in the periodic table. right? Right here, you see it here. Sometimes you might see it, just placed anywhere flying on this periodic table. So hydrogen, we do not have a proper position for it. I'll tell you the reasons. Of course, we have a separate chapter in class 11th. S block, the whole chapter is in class 11th. P block, only boron family and carbon family is in class 11th. Nitrogen family, oxygen family, fluorine family, and noble gases are going to be in class 12th. D and F block together is one chapter which is going to be in class 12th. And there is a very important property that D block elements show, which is formation of the coordinate compounds, which is again a separate chapter which is dealt in class 12th, right? So, moral of the story. Moral of the story is we are not going to talk about very, very specific properties. We are not going to delve deep into the exceptions. We are not going to talk about separate physical and chemical properties. The agenda of the session and this chapter is that you get aware of the ingredients so that the recipe can be easily ready. So the ingredients are that there are periods, 7 periods, there are groups, 18 groups, there are blocks, 4 blocks, and where to place what element. If that much is clear, things are going to be very easy. Then there are going to be certain trends that we are going to study, keeping in mind this modern periodic table. Okay? So hence today's session is one of the very important chapters of the whole chemistry that we have, because today you will know where to place what element, right? So if you observe that when I'm talking about periods, we have 7 periods, and I just told you that highest principal quantum number will give us the fair idea of the period number. All right? But what is the striking thing that I want you to observe here is, everybody, follow it. Can you see something special which is happening when 6 is flashing and 7 is flashing? These guys out here who could not find a proper seat inside the above S, P and D block category is placed like somewhere outside. And something strikingly important here is that when 6th period is getting flashed, the first line here is getting flashed. And when 7th is getting flashed, this row is getting flashed, right? So this I want you to observe very carefully right here. Okay? Next thing which I have already told you are blocks. So there is S block, P block, D block, F block. So let's see now the blocks one by one. So if I talk about S block elements, you can see the first 2 groups, group 1 and group 2, lie under S block elements. So first one, which is group 1, is alkali metals. Okay. Observe hydrogen is given a separate color. Okay, please observe that. All right. And the electronic configuration, if I talk about, yes, hydrogen fits in because of the electronic configuration, which is NS1, which is 1s1. Hence, hydrogen is here. But if I talk about the behavior, it is not going to behave like the other alkali metals. Okay. So we will talk about exceptions later. We'll talk about lithium also later. We'll talk about hydrogen in details later. But I want you to get a picture right that because of NS1 configuration, you see the whole picture the way it is. Okay. Next is the alkaline earth metal. Like the name suggests, must be present in the earth, right? Are there exceptions? Of course. There will be. We will talk about that again when we will be talking about the specific chapter S block elements. But right here, I want you to see that all belong to NS2 electronic configuration. So electronic configuration is playing a key role here. Similarly, let's see the P block elements. So if you see P block elements, we have boron family here, group 13. The name that we have given to this group is Icosagens. You would not see it commonly, but if it comes, you should be well aware of. Hence, I'm giving you the name. But what is important is the electronic configuration, NS2NP1. Next, you see crystallogens. So if I talk about crystallogens, the name, why the name is there, we will talk about that later. Again, if the name comes, you should be well aware. But yes, for group 13 and group 14, the common names that we use is the boron family and the carbon family. So the electronic configuration should keep getting in your head. The third one is pnictogens for the nitrogen family. This is very much used by IUPAC nomenclature also. It recognizes the name of the nitrogen family as pnictogen because these are the poisonous compounds. Are all of them poisonous? No, but that's how the name has been derived. The electronic configuration is NS2NP3. Group 15, nitrogen family. Then we have chalcogens, ore forming. Okay, NS2NP4, also oxygen family. Next is halogens, salt, gens forming, salt forming, which is why NS2NP5 is the electronic configuration. Group 17, fluorine family. And the last but not the least, we have noble gases, group 18, NS2NP6, completely filled subshell, you can already observe. Hence, noble is the name. That means they're inert. They don't really react. They're very less reactive or least reactive. So together, S and P are called representative elements or main group elements. We have D block also. We know that in D block, how many in D orbital? I should not say d orbital. We know that one d subshell, if I talk about, we have 10 electrons coming, right, in one d subshell. So, of course, there should be 10 such groups. You can clearly count that there are 10 such groups, right, starting from group 3 to group 12. And what is the electronic configuration in general of D block elements is N minus 1 D 1 to 10 NS 1 to 2. So electronic configuration is very important, and rest some properties coming in front of you which I want you to just see, observe and not get mesmerized with. Okay, so I want you to see that the electronic configuration is important here. Some words coming your way like colored ions. How do we know colored ions? Paramagnetic, love towards magnet. That means they're attracted to magnet. Are all the elements of the D block elements attracted to magnet? Are all of them colored? No. There are exceptions, of course. Why there are exceptions? Again, we will not talk about it in this chapter, which is the introductory chapter to different blocks, different periods, different groups. Hence, we will not get into the subtle details of it. Hence, observe it. Why variable oxidation state? We will not talk about it right now. Why they act like a catalyst? We will not talk right now. Why they are attracted to magnet? We will not talk about that right now. Are all of them paramagnetic? No, that's not the case. Are there exceptions? Yes, there are many exceptions. What are the reasons to those exceptions? Hold on, okay? So questions would arise in your mind. I'm glad they are arising in your mind, but answers has to come where they are destined to come, okay? So one question that I want you to know and answer right now is transition elements. This I want you to be well aware of. So why are D block elements called transition elements? The reason is very important. You will see S block, you will see P block, and as we are moving from S to P block, the properties are changing. There are striking changes in the properties that are going to come. What are the properties that are going to change? Hold on again. That will come in this very chapter itself. So D block elements form a bridge between the chemically active elements of S block, which you can easily understand by the level of knowledge that you have right now, and the less active elements of group 13 and 14. They are hence called transition elements. All right. So there are some differences in the properties of S and P, which is being bridged by this D block. Hence, we are calling this D block element as nothing but transition elements. Exceptions in D blocks are there. This zinc, cadmium, mercury will show a lot of exceptions to the rest of their brothers. The reason being it has fully filled electronic configuration, right? So they are not regarded as a true transition elements, okay? Only because of the electronic configuration, they are placed where they are. But if you see that their properties, they will vary very, very differently from the rest of the D block elements. Now I want you to see F block elements. These poor guys out here lying just at the low, just at the leg of it. Now the interesting part is their electronic configuration. Okay. Observe La out here. Atomic number is 57. Also, I want you to observe AC when I will show it to you. If I talk about lanthanum, okay, the electronic configuration looks something like this. It can be written as xenon, 6s2, 5d1. Ma'am, how do we know? You will know. Please hold on. You will know it very well. But I want you to focus here that electrons have still not started being filled in the F orbital. They've still not started being filled in the F subshell. Yet we are placing it with the F block elements. Why this injustice with La? All right. The elements starting from La after this are called lanthanoids. Okay. But if I tell you in technical terms, the position of La is bit ambiguous. So do not get confused where La should actually be placed. Should it be placed with D block or with F block? You will see both at different places. If I go by the electronic configuration, it should be placed with D block. If I go with the properties, it should go with F block. Hence, there is anomalous in the position of very element La, which is 57. And similarly, we have AC, okay, which has the electronic configuration as little different. So it is radon, 7s2, 6d1. Again, please observe the electrons are not getting filled in F. But what is important when we are talking about F block elements? N-2 F1 to 14. There should be electron entering in this anti-penultimate shell, which is N-2. So valence, there is penultimate, there is anti-penultimate. Okay. Now observe this. N-2 F1 to 14, N-1 D0 to 1. So this is interesting. Okay. So keep that in mind. Why, what? Okay, that's good to have curiosity. It will cater on one by one. Okay. So why are lanthanoids and actinoids called inner transition elements? Well, in case of lanthanoids and actinoids, the last electron added to each element is filled in F orbital. Okay. These two series of elements are called inner transition elements. You can see that when I was talking about D, we can talk about penultimate shell, N-1. Here we are talking about further inner to the transition. That means N-2. Okay. So hence they can be called as inner transition elements. Now I want you to observe this thing that we have already talked about, transuranium elements. Whatever is coming after uranium. Where is uranium? Let's find out uranium. Are you successful? So these are called transuranium elements, right? So now the question that might strike your mind is from where the names of the elements are coming. right? So let's cater to that important question, that how are elements named in periodic table? They may be named on the name of the scientist. We may have names based on the names of planets, Greek mythology, maybe the place of discovery, or maybe the meaning of the elements with its behavior. Okay, so how are elements getting their name? Might be different things. So for example, if I talk about the place of discovery, americium, germanium, europium, francium got their names, right? Then if I talk about the planets or stars or maybe the Greek gods, we have Mercury, Neptunium, uranium, plutonium, helium, right? Then if I talk about, of course, the name of the scientists, borium, curium, einsteinium, mendelevium, rutherfordium. If I talk about how elements got their names, elements are also named based on their behavior. Like hydrogen got its name because it forms water, right? Hydrogen, water forming. Rubidium is named so due to its deep red color, ruby color. Due to the faint glow in air, phosphorus got its name, right? So these are important things that you should keep in mind. But many a times there is a battle that happens because of what name we should give. Like a small baby is born nowadays, like the name is decided way before. But yes, in the previous times, there was a pet name given to the child, to the newborn, till the time the name giving ceremony happens. So here the name giving ceremony is done by nomenclature, IUPAC nomenclature. This IUPAC does the nomenclature of the elements, but this is a long process. Till then, we have to give the new element some name. So how do we go about when we have to give a name? We follow simple systematic rules. The simple systematic rules, the need is, of course, like you know that there might be a fight over some element. For example, this element 104, there was a fight. No, this should be the name, that should be the name. So before that stage comes that we are certain that this is the name to be given, we address it by simple systematic rules. So of course, above 100, we have the need of these rules. So how do we call the different elements? Let's say the elements which are yet to be discovered. Let's say we discover 124th element. What name should we fix? That will take a long time. Okay, so till then, how do we call it? 124 is the new element that we discovered. Ooh, congratulations. So 1, we will call it un. Okay. For 2, we call it bi. For 4, we call it quad. And we just add ium. Simple. Un, bi, quadium. If I have to give it an abbreviation, you will see that no alphabet is repeating itself. Right? So if I have to give it an abbreviation, it will be U, B, Q. So if I am saying UBQ, means we are talking about 124. So you can see 101, un, nil, nil, un, nil, un, ium. Un means 1, nil means 0, un means again 1, ium. So do you understand that? If you know nil, un, bi, tri, quad, pent, hex, sept, oct, n, the job is simple. All that you have to do is, let's say 136 un, 3 is tri, 6 is hex, and then ium. Simple, as simple as that. This is real fun. This is sheer fun. Let me give you some fun. Can you quickly tell me for 135? Quickly. Let's see. With the rapid fire, with the speed of light. Come on. 135, the IUPAC name, according to the systematic rule. As simple as that. It's fun, like I told you. Right? So, this is un. This is tri. This is pent. Ium. Quickly give me the abbreviation. Quickly give me the abbreviation of 135. It is going to be U, P. Right? Interesting. Next one, 122. You do not have to give me the whole name. You just have to give me abbreviation for 122. Give me abbreviation for 122. Quickly. I don't want the whole name. I know you can do it. Let's see. Quickly. 122. Unbibium. So UBB. That's interesting. Next one. Which will be the atomic number of the elements with IUPAC name? Pentium. Time starts now. Come on, let me see. Let's see who gives the quickest answer. So a lot of quickest answers already my way. Pentium, of course, 115. As simple as that. Okay, so now the serious part of the chapter, let's enter that. Okay, till now everything was very easy. It was fun. It was simple. Nothing difficult. We have done. There are 18 groups. We have done. There are 7 periods. We have done. There are 4 blocks. We have seen the importance of electronic configuration in deciding the whole picture of periodic table. But let's take it further. What is a group? It is a column of elements in a periodic table of the chemical elements. What is a block? It is a set of adjacent groups in the periodic table. What is a period? It is a row of elements in the periodic table. So row, column, we have already understood. Now adjacent groups together, we have seen that they can be placed and called as a block. Okay? You should know which element is placed where if I give you the atomic number. So for finding the block, it is very easy. Write the electronic configuration of the element. The subshell in which the last electron enters is the block of the element. So whichever is the valence shell, the electron is entering whichever shell will be the block, whichever would be the value of the azimuthal quantum number L. Okay, whatever will be the L will be the block. Block is easiest. Finding group, if it is S, interesting. NS1, NS2. We have just 2 possibilities. If it is D, you have to add 2. That, of course, came from NS1 and NS2. If it is P, then you have to add 12. Okay? 10 for the D and 2 for the S. But you can see that you can either do it number of electrons in P plus 12, or you can do it in number of electrons which are in the outermost shell. That includes S. Okay, I'll just help you in understanding it further. So number of electrons in the outermost shell means NS, whatever electrons are there, and NP, whatever electrons are there. So this plus 10. Okay. Then in D block, the group number will be the number of electrons in the outermost shell plus penultimate D shell. That means N minus 1 D, whatever electrons are there, plus 2, basically. Hey, what about F? Do you remember when I showed you the periodic table, I have very well mentioned that something intriguing was there. Right? Isn't it? Let me show it to you. So see out here. Look at this. You can see that lanthanide and actinides are a part of group 3, right? So for F block, if the group is asked, it is very, very clear that they are group 3, okay? Clearly you can see that they're lying in the group 3 and they're an extension of it. Also, you can celebrate the moment you get some F block element because the group will come automatically. F you get to know automatically, right? Because the electron, whichever is the last shell that you're filling, while maintaining the Aufbau rule, right? But period, how to find, which we answered very easily in the initial part of the starting of the modern periodic table only, that the principal quantum number, the highest principal quantum number will decide. So without a delay, let's get started. How to place an element? What is the role of element? What is the role which is going to play the most important role? Electronic configuration. So how I want you to write and understand, I am giving you the very important trick which will help you in atomic structure here and chapters yet to come. Okay, how I want you to write is, please write SSP, SPS, DPS, DPS, FDPS, FDPS. Vigilant, everybody. Please focus here. SSP, SPS, DPS, DPS, FDPS, FDPS. Clear? Now, which is the principal quantum number, the starting principal quantum number for s orbital? It is 1. So start writing 1 because you know 1s exists. So start writing 1 from first s and just keep writing 1, 2, 3, 4 and so on till you're finding the s here. So 1, 2, only in front of s I'm writing 3, 4, 5, 6, 7 and 8. Okay, what have I done? We know that 1s exists. So 1 is the n, which is the principal quantum number, which exists for L equal to 0, which is for s subshell. So I have started 1 till 8 for all the s that has come my way. We know that there is nothing called 1p, but there is something called 2p. So we start writing 2 to the first p and then we keep increasing. So 2, 3, 4, 5, 6, 7. Okay. Then we know there is nothing called 2d, but there is 3d. So the minimum n, that is the minimum principal quantum number that we can give for the d subshell is 3. So I start writing 3 here, 4, 5 and 6. Then we know there is no 3f, but there is 4f. So the minimum quantum number, which is the principal quantum number n that we can allot to f subshell is 4. So I start writing 4 here and 5 here. Okay. SSP, SPS, DPS, DPS, FDPS, FDPS. Okay. Then I have started for S1 till 8. Then I have started for P 2 till 7. Then I have started for D 3 to 6. Then I have started for F 4, 5. Okay. Now what am I doing? Observe here. Please focus here. I want you to write it also, but do not miss it. I will give you enough time to write this trick, but I want you to focus here right now. Look at this. How many electrons can be adjusted in 1s plus 2s plus 2p? 6 plus 2 plus 2. So 10. 10 here. Similarly, 3d, 4p, 5s. So I'm basically grouping things, okay? Just, I'll tell you the reasons. So I'm grouping things here, 18, okay? 4d, 5p, 6s. 10 electrons can go to D, 6 electrons can go to P, and 2 electrons can go to S. So I can write 18 electrons can fit in the total 4D, 5P, 6S group. Similarly, here how many? Quickly. 4F, 14 electrons. 5D, 10 electrons. 6P, 6 electrons. 7S, 2 electrons. 14 plus 10 plus 6 plus 2 gives me 32. That's right. Okay? And so is here, 32. So what have I done? I have written SSP, SPS, DPS, DPS, FDPS, FDPS. Then I have written numbers according to whichever the principal quantum number is the smallest that can go with the L, which is SP, D and F. And I have kept increasing. This is what I've done. Then I have grouped things together. Okay. Now I also want you to remember all the noble gases. Helium, neon, argon, krypton, xenon, radon. I want you to know their atomic numbers also. 2, 10, 18. Then we have 36, 54, 86. Right? Now I want you to become extra vigilant wherever noble gas electronic configuration is coming. Please observe here 1s2, so I can write here helium. Similarly, 1s2, then the next one. Only helium is having the electrons coming in 1s2, rest all will be p6. So 2p6 is neon, 3p6 is argon. You doubt me? Okay, it's good to doubt. You can see, please count electron 2 plus 2 plus 6, 10. That is why I grouped the whole thing so that it becomes easy for us to remember. Okay, 10 plus 2, 12 plus 6 electrons in 3p. So wherever I'm writing helium, that means after the electronic configuration is done in the whole subshell. Okay, so 3p6 is done, we have argon. That means 18 electrons will be covered up till here. Similarly, 4p6, of course, we are going to have now helium done, neon done, argon done, krypton. Similarly, xenon here. Similarly, radon here. Okay? We are leaving 7p6. That's the last one. Okay. Sorted. How do I use this information now? The using the information is the most important tool now. So to utilize this whole trick, first observe it, then only you can utilize it. SSP, SPS, DPS, DPS, FDPS, FDPS. I have written wherever the electronic configuration of noble gas was coming. I wrote it, okay? And this is something that is prerequisite, that number of electrons that can enter S subshell is 2. Number of electrons that can enter P subshell are 6 total electrons. Number of electrons that can fit in D are 10 electron. And number of electrons that can enter F are 14 electrons. F subshell total. In one orbital, only 2. But in whole subshell, we know this is the rule. Okay? This is the prerequisite. The knowledge of N, L, and the whole electronic configuration is the prerequisite. Question the way it will come is like this. What is the period, group, and block for cesium 55? What do? We go to this trick that we have done right now. 55 means somewhere near to xenon. So what do? We reach xenon. Xenon is 54. Okay? So xenon is 54. That means that till here it is 54. Okay, till here 5p6 it is 54. We know how to go about. We write the noble gas configuration. Whatever the noble gas is, we write that. Whichever is the closest one. Xenon is the closest one. And then we keep filling the electrons. So next electron will go to 6s1 clearly. Xenon is here. 6s1 is here. So let's see it right. Okay, so 6s1. That means that the highest n that we have is 6. So it is 6th period. The electron is going to S subshell. That means it is S block. And number of electron which is entering the 6s is 1 electron. So it is group 1. Very easy. For S block, it was pretty easy. So cesium should be in 6th period, S block group 1. Let me check. Wonderful. We are on absolute right track, isn't it? Let's check the next one. Bromine atomic number is 35. Let's go to our trick and let's see. So if I go to my trick, you can see that 35 means before krypton, okay? Before means we have to look at argon here and after argon. So whichever is the electronic configuration before it, you are not supposed to write the electronic configuration of that atomic number which is next, but electronic configuration of that noble gas is to be written which is before the element concerned. Okay, so let's see. We have argon. We write argon. Okay, then what do we have? let's start using that information. So argon, then we have 4s2 3d10. That means 18 plus 2 plus 10 plus, so look at this. I have to reach 35. So 18 was here. 18, 19, 20, 30, 35 means 5 electron has to come to 4p. All right. So that means 4p 5 makes it 35. Super easy. Job becomes very easy. You can clearly see the highest n being 4. That means period is 4. Of course, you can see that the electron, the last electron which is entering is the p subshell. So that means p block. Of course, you can see that the highest n, the outer shell, has 5, 6, 7 electrons. You just have to add 10, okay? Or I would suggest rather to use the number of electrons in P, okay, plus the remaining, whatever is in D and S. So plus 12, okay? So how do we go about when we have electrons in P? You can go either ways, number of electrons in P plus 12 or number of electrons in P and S plus 10. Whichever is convenient. I'm going to use this thing only, number of electrons in P, which is 5 plus 12. So I get 17th period. Oh, I'm so sorry, 17th group. So everything is sorted. It should be 17th group. Yes, it is. 4th period. Yes, it is. And the block is, of course, P block. Let's see the next one. You're connecting the dots, making it very easy. Let's see, okay? Let me bring the trick near to me and let's use it. For the next one, you do not need the trick only. I'm sure you know already. Argon 4s2 3d1, you remember? So the last electron is going to D subshell. So it is D block. Whenever electron is entering D block, you just have to add 2 plus the number of electrons in D block will give you the group. So it is third group. And of course, the moment we know that we are talking about highest N4, then it is fourth period. Super simple, right? Easy. The trick, have a look at it, get a hang of it. It is going to be life savior for you. All right, let's see this question now. The elements with atomic number 2, 10, 18, 36, 54, 86 are called. I just gave you this trick and indirectly you know the answer. Right? What is the answer? Option A, B, C or D? Of course it's A. Right? Do not get excited the moment you see noble word. Noble word might be misleading. Noble metals. There are certainly some metals which don't react. Gold, silver, to name a few. Do they not react at all? No, that's not the case. We're not talking about extremities here. We're talking in general here. So noble metals is not something that should entice you. Be very careful, be mindful, and hence the right answer is option A. Okay? Now let's see the next one. The element EU, europium, with atomic number 63 belongs to. I want you to become very vigilant the moment any F block element comes. Okay? Right now, let's say I do not know it is F block element or it is D block element. Okay? It might be F, it might be D. So, if it is F block element, we know for a fact that it has to be third group for sure. So, if F block is written and fourth group is written, strike that immediately. Immediately. F block third might be your answer. F block fourth cannot be your answer. Don't get enticed by F block and some other group other than 3 is given. Okay, that can be striked off immediately. Right now, let's say I do not know it is D or F. Hence, we will find out the electronic configuration. We will use a trick. Let's say there is another option which says F block, fifth group. Do you understand? You do not have to even go about solving it. Then the job is clear that F block, okay, has to be group 3. So if any of the one options has it, we know the answer. So right now, answer has to be option B or C. If you have a fair idea that europium is F block element because you've fairly seen it, because you have pasted the periodic table in front of your desk and you keep looking at the elements, and hence you know that europium was somewhere down. And if you remember your picture memory crystal clear, you can mark the answer without even using the trick. So you know the answer would be C. But let's say I don't remember, I did not follow what ma'am said, and I did not paste the periodic table. My picture memory hence is weak. Hence, I have to use the trick. Okay, so let's use the trick. We have, what is the Z under consideration? 63. So let's see, we know that till here it is 54. 54, 55, 56, 56. We have to reach where? Please observe, we have to reach europium, which is 63. We have to reach 63 is our target, okay? Okay. 54 is sorted. 55, 56 is sorted till here. 56, 57, 58, 59, 60, 61, 62, 63. 4F7. So if I have to talk about 63, we know that we can go to xenon. After that, we keep filling 6S2, 4F7. What does this suggest us? That the last electron is going to F subshell, right? Which means that the orbital which is being occupied is this n-2 subshell. And if I talk about F, look at this, it is having half-filled electronic configuration, must be stable. Also, I want you to observe that the moment F comes into picture, we know that for a fact that it is third group, but also look at the highest n, which is 6. So highest n, which is 6, is going to be the period. So answer has to be 6th period, F block, third group. Right answer is already away, option C. Cool? Okay, the question is, if one electron is to be removed from gold atomic number is given, it will be removed from which of the following orbitals? Okay, 79. We know till xenon. Please look at this. 54, 55, 56, 56 plus 14, 60, 70. Then we know 5D, 10 means 80. So we have to fill 2 electrons less here to reach 78. So we know that the last electron is entering D subshell. We know it is going to be D block. We know that the group number will be D, whatever number of electrons, plus number of electrons in S. So that will give you the group, or simply whatever electrons are coming through this trick. All right, through this trick, mind you, plus 2. So what I mean from here is there is an exception coming your way. Gold, which is 79. Okay, yeah, we had to reach 79. So yeah, doesn't change anything else. Now, when I say gold is 79, that means we have xenon, 6s2, 4f14, 5d9 as the electronic configuration. Please observe one thing, that we can always play around with this kind of picture. How can we play around with this? We know that S always compromises, and we can give 1 electron to 5D. So if I write it in increasing order of n, I can write it like this. Isn't it? So 1 electron from 6s can actually be brought into 5D, and we can write 5D10 because of the same reasons as chromium and as that of copper. Fully filled and half filled electronic configuration. So there will be exceptions. You will see one such exception in platinum also. Not always where you see fully filled and half filled electronic configuration giving you exception. Somewhere otherwise also you might find exceptions, but that will not change anything that we need to find. So if you're careful about the trick, wherever it hinders, use your common sense and that will guide you through the needful. So this trick, exploring this trick is your homework. Please try it at n number of questions. Try it with different elements, pick them up and try it out. Okay? For example, gold is very important. So I can write xenon 4F14, 5D10, 6S1. If you ask me which is the block, you know, while filling, please, don't ever do it. The block, the period, the block, period, as well as group, you must always do while filling and you must always judge. But for removing an electron, please arrange them in higher order of n. If there is a tie, then higher order. Let's say we have ns also and np also, then of course ns and then np and so forth. Okay? Now, look at this very carefully. The last outermost shell is 6s here. So the right answer has to be 6s only. Even if you would not have been knowing that there is some sort of change here, you would have given the right answer. But I want you from the very question to become vigilant about all the exceptions there are. Okay? And you will find many exceptions. Platinum, just check it out, right? This brings us to the end of the session. I want you to go back, look at the mindful question. Which radioisotope is used in the ionization smoke detector to ionize air? You have seen the smoke detectors in schools, in offices, in airports.